Hello, my name is Gan Li, and I'm the TA for CE318. Now I'm doing this video for the tutorial to show how to solve those problems in ANSYS. We're doing this tutorial because we don't have enough seats in the computer lab. So let's get started and follow those steps to solve those questions. I will show them step by step. So first step, go to Start, Numerical Methods, and choose an ANSYS product launcher. Takes a while. There we go. Simulation environment, choose ANSYS. The working directory is a place where all your work will be saved. You can choose a folder you like. For me, I'll choose ANSYS. No. Okay, I choose 318. And job name, question 1. Okay. And go down. I cannot go down. Click Run. It'll bring you the answers. Also takes a while. Okay, notice this window. This window is an output window. It'll record all you have done in ANSYS. They have the record here. Just don't close this window. If you close this window, ANSYS is gone. So minimize this window. Okay, here we got the answers. The first line is the manual, main manual, and the second are those toolbar. You can also find in Word. So those buttons, the first two are very important. These are Save Database, Resume Database. This is where you can save your work and then resume from your previous saved point. Let's get started. First, we are going to get the preferences done. So we choose structural. So that'll give you best menu for structural problems. Click OK. Go to preprocessor. We choose the element type. So in question 1, it's a bar element, apparently. So we add, click add. We choose a bar element, choose link, and 2D spar. That's what we want. You can click apply or click OK. If you click apply, this window is still here. If you click OK, it's apply and close the window. So if you want to know more about the element, you go to help. And then you search for spar. I got link 1 here. Double click. This is a link 1 geometry. Have 2 node. Okay. Those are input summaries, output summaries. We'll use that later. Just minimize it. Okay, we have selected the type 1 element. Cancel. Close. The real constant is the real constant of your element. So add. This is the link 1 we have selected. Click OK. For this type of element, the constant would be the cross-sectional area. Okay. Cross-sectional area is 2000 millimeter square. So that's 2000. Notice that in ANSYS we don't have the unit system. So you have to keep all the unit consistent. If you use SI units, you use it all the way. If you use inch pound units, you use it all the way. So click OK. Close this window. Then we go to material properties, to material model. Choose structural, linear, plastic, isotropic. The EX is the Young's modulus, and the PRXY is the Poisson's ratio. In this problem, we have the E. It's 200. Click 200. The Poisson's ratio, just leave it at 0. Okay. Close it. Okay. Since now we have done the element type, real constant, and the material properties, so it's a good idea to save your work. Remember that we don't have the redo or undo in ANSYS. So once you do something wrong, you cannot cancel it, you cannot undo it. You have to go back to the checkpoints you have saved, or you can correct your wrong operation. Well, let's continue. Next thing we do is to do the modeling. It's actually drawing the picture of this picture here. So here we first need to draw some key points. This is 1, 2, 3, and 4. So we need 4 points basically. Okay. How about set the origin at point 2? Alright. Create key points in active coordinate system. So point 1, okay, is x is 0, y is 3000. Click apply. Okay, then input 2, number 2 is 0, 0. Click apply. Number 3 is 0 and minus 5000. Apply. Number 4 is, okay, it's 4000. It's 4000 and 0. Okay, click OK and close it. Okay, here we can see we got 4 key points. Then we create the lines between the points. So create lines, straight lines. So this is a pick box. Use it, click, line we got. Okay, just like that. Click OK. Alright, so this is the geometry of the first question. Next, we need to do the meshing. To do the mesh, here actually we don't cut those elements into small pieces. We just use one element, because here this tight bar is actually one element, right? So we need to manually set the size of the element as just one piece element for each bar. So we go to size controls, and a manual size. Lines. You can pick lines or just select all lines. Okay, we have two different ways of setting those element size. One is to set the size of the element, the length. The second way is to decide how many elements you want to apply to each line. So we use the second way. Just one for each. Click OK. Alright, here we can clearly see those lines have been changed. Okay. After we decided the size, we move to mesh. Click lines, select 1, 2, 3, and click OK. Okay, it has been meshed. So how we know that? We could go to the list, the elements. See, we've got 3 elements, right? And if you want to know the numbering of those 3 elements, just simply go to plot and multiplots. Oh, it doesn't show the number. Okay, we go to plot control, go to numbering, or we can turn it on and off about the numbering of lines, areas, and so on. Okay. Next up, we need to apply the loads. In ANSYS, like the restrictions or the forces, they are all called loads. And okay, loads, we define loads, apply structural displacement on key points or on nodes, because the nodes are the same place with key points, right? Okay, we pick 1, 2, 3. They are fixed in both x direction and y direction. Click OK. Okay, so we see those constraints have been applied. Now it's time for force and moments. Okay, go to force on key points. Just click this point and OK. So it's in x direction towards the positive way, so we input positive 10. Click OK. See this red arrow? Alright, it's basically done about the setting of this problem. Now it's time to solve it. Solve. Current loading step. Click OK. Woohoo! Solution is done. And just close it. You won't see any change from the interface. That's because we are going to check the results by selecting General Post Processor. You go to General Post Processor and go to Plot Results, Deformed Shape. So you can change deformed shape only or deformed and undeformed. Click OK. Well, the white lines show the original place, and the deformed ones the blue one. You can even show the animation of that whole process. So just go to Plot Control, Animate, Deform Shape. Right? Deform a. Click OK. it will show how this whole system is deformed. You can adjust the speed and click forward on it. That's pretty interesting. You just stop it and let's move back. Close it. So anytime you want to refresh your window, just go to Plot, Multiplots. Right. So in the question, we go back to the question. In the question, we need to calculate, we need to know the actual forces in the bar. All right. But before that, we have to make sure that it looks right, because from the deformation, it looks right. And how about from the reaction forces? Let's go to List Results and Reaction Solution. All items. Click OK. So we can see Fx and Fy. I think the Fy, summation of Fy should be 0, and summation of Fx should be 10. So that's absolutely right. Okay. Again, if you want to know the numbering of the node, you can go to the plot control, numbering, and turn on the node. Click OK. There we go. You can see the numbering of the node and the forces here. Okay, just close that. But to know the actual stress in the bar, you need to go to the help. This is the output definition. So if you see here, this is actual stress in the element, which is named SAXL. Okay, and if you go down, you see SAXL and the output command, and those this is sequence numbers right here. Okay, we're gonna use that to output the actual forces, stresses. Okay, here we go to the element table. First we need to define it. Click add. So remember the name of that? It's capital S. I couldn't remember. Go back. SAXL. SAXL. I use sequence number LS, and here 1. Click OK. Now it's defined. Close it. So if we list the element table, you can see SAXL is defined here. So click OK. You may okay, notice that here this is a numbering of the element. This is stress in a bar. So for 1, 2, 3, we got 3 stresses. So remember to turn on the numbering of elements. Plot element doesn't show the numbering, so we go to numbering for elements. Oh, here we go. Element numbers. Okay, there's 1 and 2. Okay, exactly 1 and 2 here. So the first question has been solved. And by the way, if you want to print the screen here, you probably want to go to report generator. If you click it, click OK. See, this report is also created in the directory. Yes. Okay, you got a white background to save the ink. You click this capture. Well, let's do that. Click OK. Close it. Right? And just save it. I forgot to save it. Just make sure you guys save it before you solve it, right? Okay, just close that. Just save everything. Click OK. Alright, if you go to the directory you have defined, which is CE318. Okay, you got question report. This is an image we've captured, and these are the database, right? And this is the animation. So you got everything here. So that's so much for the first question. If you guys have any questions, you can come to me and ask me about the details or whatever questions, difficulties you have encountered when you operate this software. So let's move to the second question. It's also a 2D problem. Okay, for the second question, we will basically follow the same process. First, we need to choose the elements. So here, the elements we want to use is a solid element, because we need to cut the whole piece into small pieces, right? Okay, so we still use this working directory, and I name it question 2. Let's make sure the simulation environment is ANSYS also. Just run it. It's kind of weird talking to this computer. Well, I hope you guys don't mind my mistakes. Okay, this is question 2. You can see from the title bar, right? We'll move a little bit faster here. Structural, click OK. Processor, select the element, add, choose solid. Here we have different solid models. We have like 2-node and 8-node. Well, here we just select 4-node. It's good enough, and for 8-node maybe it's more accurate, because the 8-node will give you the edge, which can deform quadrilaterally, not only linearly. But here we just use 4-node here. Let's click OK. close it, go to row constant, add, click OK. Okay, we don't have any row constant for that. Okay. How about the thickness? Well, for the thickness, I think here we don't need to use the thickness because this stress here has been told, like in stress, it's not force. If it's force, we need to use the thickness, but here is stress. We just simply think the thickness is 0, and we directly apply the stress on the edge of this plate, right? Okay, just cancel that. Material properties, go to models. It's the same thing. Linear, elastic. Okay. E is 10 power 6. It's 10 power 6. Poisson's ratio 0.25. Click OK. Close that. Now remember to save it. Alright. So the next step, we need to create the geometry of the whole thing. And notice here we are required to use symmetric or anti-symmetric lines. So we can do it a quarter of the whole piece because it's a symmetric vertically and horizontally. So we take quarter of that. So for 1/4, my idea is to create a rectangle, right? And take this corner out. Then we get the geometry of a quarter. Okay. So we go to, remember to save it. Go to modeling, create, just directly create the areas, rectangle, by 2 corners. Okay, we put 0, 0. Whoop. But 2 corners. Oh, it's kind of select here. Okay. This is the first corner and the second corner. Well, it's not accurate if you just draw your cursor on the screen. It's better to input the width and the height here. So the width is 2, the height is 4. So this is 2, the height is 4. Click OK. Okay, what if you done something wrong? If you draw this rectangle, it's wrong in size. How we do that after? Okay, one thing you can do, just resume database. It's all gone. And back to the checkpoint we have saved, right? That's how we play the computer games. Well, the second thing is to do the correction. Okay, if you just randomly draw a picture here. Okay. You just can do the correction. under modeling. This notice here, this is create, and we got the delete right here. We can delete the areas here. Click OK. There we go. And create again. 2 corners. So 0, 0. The width is 2. The height is 4. Okay. Again, we need to create a circle. Solid circle. The origin is this point here. Also, you need to input. It's more accurate if you input here. So the x is 2, y is 0. The radius 0.5. Oops. 0.5. Click OK. Alright, now we need to take this circle out. So we go to Operation, Operate, and choose Booleans. Use Subtract. Areas. Subtract areas. Okay, we need to pick one area which we want to subtract from. Click OK. And second, we're asked to pick the areas again. This time we pick the area we want to subtract. Choose this circle. Click OK. Now it's gone, right? And save the work. Next, we need to do the meshing. Okay, in this example, we really want to mesh those plates, mesh this plate into different little plates that we call elements. So we can do size control and meshing together in the mesh tool. Here we got the smart size. If you click it, you'll see you can move this square back and forth. That will give you a finer meshing and a coarse meshing. For fine mesh, it takes more time to compute, but it's more accurate. For coarse, it goes fast in calculation, but the result is coarse. So I'll take 4. You guys can take 3 or 2 if you like. Meshing areas. I don't have the checkbox in this display, but you guys can see from your Windows computer. Choose the quad areas. Click mesh. So select this area. Click OK. Now you can see this whole piece is perfectly divided into 3 pieces, 2 small pieces. Okay. After that, we need to do the forces. Okay, here we notice that we have the stress up and stress down, but we only take 1/4 of that, right? So we only apply the stress on top. And for this line and this line, it's a symmetric line. So we go to load, define loads, apply, structural displacement. Here, this is a symmetry boundary conditions on lines, and we choose this line, the bottom line. Click OK. We notice that here is a small s here, and we go back and apply force. Here we got a pressure. Yeah, apply pressure on lines, top, and click OK. Here we need to input a constant value, and in ANSYS, the pressure we have in ANSYS we have the definition of the pressure. When the pressure goes against the surface, it's positive. When the pressure goes out from the surface, it's negative. So here, the pressure goes outwards, not into the surface, so it's negative. Okay, let's try it. So it's 10,000. It's 10,000. Click OK. Well, I said it wrong. Well, when the arrow goes against the surface, it's negative. Okay, remember how we do that? We go to resume, or we can delete what we have done wrong. So go to delete, or load. No, we just choose structural and pressure on lines, select this line and take it off. Okay. So we're going to load, define, apply again, pressure on lines, this line. It's negative. There we go. And save the work. Let's go to the solution and solve it. Solution is done. Well, again, we plot results, deform the shape. Click OK. Now you can see the shape is pretty much right. Well, when we kind of pull the plate towards up, the plate is extended in Y direction and shortened in X direction. So it looks right. Okay, here we go back to the question, see what we need to do. So we need to plot the stress and strain distribution and identify areas of maximum stresses and strains, right? So it's pretty easy to do that. We go to oh my eyes. Plot results, the contour plot, Nodal Solution. Okay, stress. Okay, if we well, I have a whole bunch of selections here. Okay, choose stress intensity. Okay, so this beautiful picture just show you where the dangerous point is and how the stress is distributed. And also we can use the Adamant solution. Same thing, we plot the stress intensity. Okay, we get the similar contour, but you may notice that the nodal solution is more smooth. It's more smooth than the Adamant solution, right? That's because the nodal solution is kind of calculated for every node, and actually the computer is calculated based on the element, based on each element. So that's why Adamant solution is not smooth, but nodal solution. Go back to nodal solution. Is smooth because it kind of average the results from the neighboring elements to one nodal solution. For example, we have a node here, and then we have 4 neighboring elements. So for this nodal solution, it kind of average the neighboring elements. So that's why we get a smooth line here. Okay. And we also need to identify the maximum stresses and strains. Okay, very similarly, again, also plot the strain from here. This is displacement and the elastic strain, whatever strain you want, right? You also can find the maximum is here, and the minimum is here. And you also get the number here. This SMN stands for minimum, and the SMX stands for maximum. But maybe you want to know for any point in this picture, you want to know the actual number. That's easy. Okay, we just plot it. Okay, if we go to query results, so you can actually query each point. Like for stress, well, x direction, if you click here, it'll give you the number. You can add an arrow, click OK. See? And for any point, just click it, give you the number, click OK. So what else we need to do? Justify your choice of mesh refinements. I think we get reasonable results from this meshing. If you want to use finer mesh, we just simply go to post-processor and mesh tool. This time we choose 2. Okay. Okay, just remesh it. Yes. All right. Then we go to solution and then we solve it again. Solution is done. We kind of plot in the query stress from this point. Well, you guys may notice it's slightly different, isn't it? It's a slightly different, but it's pretty much the same. Um, well, I would like to say the second result we have got is more accurate than the first one because of the finer meshing. But it doesn't change too much, so we're good. Okay, I think that's pretty much it. And if you guys have any question, you simply go to CE318. That's my office, and I'll be happy to answer the questions. Hopefully, it's helpful. See you.